Hi guys, so today we're going to talk about on the Regents exam what it means when you see the words in terms of atomic structure. So this means that you're going to need to be able to explain something, a pattern on the periodic table, and you need to explain it by talking about the structure of the atom in some way. Okay, so first let's talk about what all of these things mean. First, we're going to look at nuclear charge. And the symbol for nuclear charge is the letter Z. Okay. And the nuclear charge is the number of protons. So just as a review of atomic structure, the nucleus has protons and neutrons in it, but neutrons don't have a charge. So the charge of the nucleus is always positive, and it's the same as the number of protons. So let's do an example. Oxygen is +8. So this is an atom of oxygen here, and that's its nuclear charge. Okay, now effective nuclear charge, we symbol Z with a little EFF down here. So that means like my nucleus is positive and my electrons are negative. So they're very attracted to each other. The nucleus is pulling on the electrons and it's trying to pull them close to it because they have opposite charges and they're attracted, right? But the effective charge is looking at the outer shell. How much of a pull are these electrons in the second ring feeling towards that positive nucleus? So the formula for calculating this is the number of protons minus the inner electrons. Okay, so the number of protons in this oxygen atom is 8. So you would think, okay, the electrons are feeling like, oh my God, 8 electrons are pulling on me. But this layer, this inner shell right here, has 2 electrons in it that are like shielding those outer electrons or blocking the pull. These outer 6 electrons aren't feeling the pull from the nucleus as much because of these 2 electrons on the inside kind of blocking it. So you subtract how many electrons are in the inner shells. In this case, we only have 2 electrons because we only have one inner shell. So really, the charge that's felt here by those valence electrons is a +6 charge, even though there's 8 protons. So that's going to be used, the nuclear charge, to explain some things later on. The next thing that you're going to see, the next word you're going to see is shielding. And we kind of touched on that right above. Shielding is based on the number of electron shells that are in an atom. So here I have lithium, right, that only has 2 shells. Here I have potassium that has 4 shells. So there's 3 electron shells shielding the positive nucleus. So where in lithium, the nucleus is like out there ready to attract negative electrons, for potassium, it's going to be harder for potassium to attract more electrons because that positive nucleus is being covered up by 4 layers of electron shells, of negative electron shells. So the more electron shells an atom has, the more that positive nucleus is covered up and the less effective nuclear charge that atom is going to have. Finally, guys, we're going to be using electron-electron repulsions to explain things. So if I use oxygen as my example again, and I write out its electron configuration, 1s2, 2s2, 2p4, right? Now, if I draw orbital diagrams, you remember these, right? My p orbitals have 3, 1, 2, 3, 4. Okay, so when you have paired electrons, when you have two electrons in the same orbital, they're going to repel each other. You're going to increase repulsions. And when you have things repelling against each other within the atom, that makes the atom unstable, more unstable, which means it's going to be more reactive. We're increasing reactivity. Okay. So again, guys, these are the reasons that we're going to be using to explain some of the patterns or the trends that we see coming up. All right. So let's go on to that. 3 properties you need to know how they change, whether we're going across a period or down a group. Now, not to make you mad, but as always, in your Regents reference tables, you can look these up and see if radius goes up or down as you go across a period or down a group. For you guys, you just have that one periodic table with barely anything on it. So these are trends that you guys are going to have to remember, okay? Atomic radius is just the size of the atom. So if we picture the atom being a circle, it's just how big it is, right? Electronegativity is the attraction for electrons. So it's how easily something gains electrons or how good something is at gaining new electrons. Ionization energy is the energy required to remove an electron. Okay, so back when we talked about metals and nonmetals, that was way back here, okay, we talked about how metals have low electronegativities and ionization energies. That means they don't attract electrons well, and low ionization energy, it doesn't take a lot of energy to pull the valence electron off. So overall, metals have a weak hold on their electrons. Low electronegativity, low ionization energy. Nonmetals having high, both of those things, meaning they have a good attraction for electrons. They attract electrons very well, which means high ionization energy. It's going to take a lot of energy to pull off a valence electron. It's not easy to pull off a valence electron because the nonmetal nucleus is holding onto them so tightly. All right. So not only do you have to know what these words mean, you have to be able to tell me how they change, whether I'm going down a group on the periodic table or across a period. So let's look at down a group first. So I gave you guys a nice little visual here. What can you tell me about the size of the atom, the atomic radius? As we go down a group, atomic radius increases. All right. Why does it increase? Why is iodine a wider atom than fluorine? Because it has more shells. And now, guys, you can't just say it has more electrons because you can add electrons to an atom without adding any shells to it. The important thing here is that the number of electrons increases so much as we jump down a group that we have to add more shells, and the shells is what make it get wider. Now, whatever the radius does, the other two things do the opposite. So down a group, the atoms get bigger, so the electronegativity and the ionization energy gets smaller. So as far as your memorizing goes, that's what you want to think about. Now, to explain why, all of the explanations are the same. Anytime you want to talk about why things happen going down a group, it's because when you go down a group, your number of electron shells are increasing. Okay. Now, this is okay. This is okay for a Regents answer. What I want to do is take it a step further with you guys and talk about how increasing the number of shells affects one of these properties that we talked about in the beginning. Okay, these are the words we want to use to make explanations in honors. Okay, so increased electronegativity. means that, decreased electronegativity. That means that iodine is worse at attracting electrons than fluorine is. So why would iodine have a harder time gaining more electrons? Why won't those negative electrons want to go to iodine as much as they do want to go to fluorine? Well, if there's more shells in iodine, that means that there's more shielding, meaning that positive nucleus that those electrons would be attracted to, it's covered up in this case by 1, 2, 3, 4, 5 layers of negative stuff. So do negative particles want to go to where there's already 5 layers of negative stuff? No, they want to be attracted to positive things. So the more shells, the worse the atom is going to be at attracting new electrons because of that shielding. The more shielding there is, the more inner electrons there are. So when you calculate your effective nuclear charge, it's going to be lower. That nuclear pull is not being felt because it's covered up by all of those electrons. All right? Same thing here, guys. Why does ionization energy go down? That means that this electron is easier to pull off than this electron. Because look how far this electron is from the positive nucleus versus look how tightly this one's being held. If there's more shells, there's less of a nuclear attraction. So easier to pull off an electron. Okay? So radius goes up, electronegativity, ionization energy go down, and all of this happens because as you go down a group, there are more shells. Just going to erase this so it doesn't look so sloppy. All right? Make sense? Okay. Let's talk about across a period. And guys, you can say this is a trend for any group. So I picked group 17 to show you a picture of, but this can be true for any group. Same thing for across a period. So I chose to show you guys a picture of period 2, but these trends would occur across any period on the periodic table. So obviously what happens to radius, if we look at the picture, the radius goes down. Whatever the radius does, the electronegativity and the ionization energy do the opposite. Okay, so notice that the trends are the opposite also of the group. So if you can remember one of these things, you can remember the rest by knowing it's the opposite. Okay, so now, why do all of these things happen? Again, guys, just like with down a group, we used shells to explain everything. Across a period, there's really one explanation that explains everything. So normally I would think, okay, as I go across the period, look at my number of shells. My number of shells is staying the same. So I would almost think all of these atoms would be the same size, right? But look at my nuclear charge. Lithium is +3, beryllium's +4, boron's +5, carbon's +6. So why do we get smaller as we go across a period? If you're increasing the nuclear charge, but keeping the number of shells the same, the attraction for electrons increases. Okay, so there's a stronger nuclear pull as I go across. My shells are getting closer together, so my atom is getting smaller. I'm able to gain electrons better. My electronegativity is increasing because the more positive protons you have, the more electrons we're going to be able to pull in. Ionization energy increases, meaning this electron is going to be harder to pull off than this electron. Why? because this electron is being held on to by a +6 nucleus. This electron's only being held on to by a +3 nucleus. So if it's held on to tighter, it's going to take more energy to remove. Okay? All right. So guys, these are just some graphs to kind of show you. Oh, I forgot we wanted to talk about this first, then we'll get to the graphs. Where are the most reactive elements? So guys, you want to think about ionization energy and electronegativity when you think about reactivity. When metals react, they lose electrons. So you want to think, well, where is the ionization energy the lowest and the electronegativity the lowest? If we think about our trends going this way and going down, has my lowest ionization energy and lowest electronegativity, meaning that atom is going to lose its valence electron the easiest and react the easiest. So the most reactive metal on the periodic table is francium. But if francium is not a choice, as you go to the left and down, your ionization and your electronegativity decrease, making the metal more reactive. Now for nonmetals, it's the opposite because nonmetals gain electrons when they react. So now you want to look for the highest ionization energy and electronegativity. So you want to go to the right and you want to go up to look for your most reactive nonmetal, your best element at gaining electrons. Right? Now you want to be very careful here, guys, because you'll be like, okay, furthest to the right and furthest up, my most reactive nonmetal is helium. Why is that not okay? Why can't I pick from anything in this column? Because these are noble gases. And what do we know about noble gases? They are stable and they don't react. So when we're going to the right and we're going up, we're stopping at group 17 and we're going up to fluorine, which is our most reactive nonmetal. Okay. As far as metallic character goes, guys, that's like how much something acts like a metal, how easily it gains electrons. So as I go across a period to the right, I'm literally going to the non-metal side of the periodic table. So metallic character is decreasing. Metals that are towards the staircase, they're much less reactive than metals that are over all the way on the left-hand side. As I go down a group, though, my metallic character increases. Those valence electrons are very, very far, 6 shells away from the nucleus. They're going to be a lot easier to remove than atoms that are at the top of that same group. Okay, so that's just something else they could ask, which is related to reactivity. All right, so here are those graphs that I was talking about. This is one for atomic radius. So you'll notice the elements right here, they're all in the same group. So as you go down a group, the radius goes up. You can see that each point gets higher and higher on the graph, right? But now here is as I go across the period. So what's happening as I'm going across each period? Here, here, here. Across a period, the radius decreases. Okay? And then this is just a chart, guys, too. And you could see the pattern, which, again, we talked about in video 1, how there are patterns on the periodic table. Even if you know nothing about an element, you can guess something about it based on where it is. And now you can guess about its reactivity based on its ionization energy and electronegativity. So here's ionization energy. And again, guys, this part of the graph, so from lithium to neon, that's period 2. So ionization energy increases as we go across a period. And then we jump down to the next period and it increases as we go across the period. But as you go down a group, what happens to the ionization energy? It decreases down a group. Now, in our next video, I'm not going to talk about it today. There are some exceptions to the ionization energy. Here we're going across a period and we see that ionization energy is decreasing. Okay, and we're going to talk about that next. All right, here's some questions. Hope you guys have a good day.